Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Good. You guys are looking good. Okay, still surviving the semester. I mean, it's been only a week. Feels a lot longer to me, but it's been only a week. Okay, so let's, we can change. Let's jump into it. So, I mean, pretty much started on time, but I had a late morning. I even just got out the shower. My hair is wet. If you know, of course you can't notice. Like, you're not going to notice with my hair. Who am I kidding? Okay. Let's get into it. So today is an exciting day. We are actually going to start calculus today. We still have something to wrap up from the last section, which it is a good segue into calculus. So in that regard, it's not totally out of the way, because it is something that, you know, we need to understand in order to fully grasp what calculus is going to be about when we start to develop certain things. But technically it's from the last section. So we'll wrap that up and then we'll talk about essentially what calculus is, because a lot of people don't know, even people who've taken calculus. And then we'll start. I don't know how far we'll get, but we will do our best. So the last thing I wanted to talk about was something called average rate of change. Cool. So let's talk about definition. So I'm going to give you the mathematical definition, show you an example, and then I'll talk about what the interpretation is, how you want to actually think about this. So let f of x be a function defined on at least, could be defined on more, but AB. Another way of saying that is for or defined for x greater than or equal to a, but less than or equal to b. Same thing I can say. So that AB represents an interval on our x-axis, right? A range of x's. All x values between a and b. Okay, so when I plug any x value between a and b into this function, it works, it makes sense, it's mathematically defined, right? So let's suppose we have a function defined on a and b. Then the average, that should be a v, rate of change of f of x on AB. So I'm defining this phrase here, is given by, there's no universal notation for this. I'm just going to call it average rate of change. Equals f of b minus f of a over b minus a. And that should be familiar to you. That's our old friend, the difference quotient. So that guy showed up yet again. But we're going to start to, if you didn't know before, we're going to start to figure out why this guy is important. Where did he even come from? So let's actually look at a picture. So what am I saying here? So let's say this is my function. This is my f of x. Okay. And let's say my interval that I care about is like here, a and b. Right? Just chosen at random there. Now, of course, when you trace up, hit that point, the corresponding y value is going to be f of a. And of course, when I go up here, hit that point, You have to make those sounds when you're drawing. It makes it better. You get more. That's a pro tip. You get more accurate. So now, what am I saying? What is that f of b minus f of a over b minus a? Well, here's one thing you can notice. Let's say I called my a x1. It was the first x value, and my b x2, the second x value. Then correspondingly, this guy would be y1, and that guy would be y2. And if I were to take, for example, if I were to imagine that there's a straight line connecting these 2 points. Someone's trying to get in here. Let them in. If I imagine there was a straight line connecting these 2 points, and someone were to ask me the slope of this line, then what it would be is, well, we all know y2 minus y1 over x2 minus x1, right? And what is y2? Well, that's f of b. y1 is f of a, and x2 is b, x1 is a. So it turns out the difference quotient is actually, it's just the slope formula, right? Believe it or not. I hope it's not anticlimactic, but it's just this old formula that we knew about, the slope. So in other words, this is just the slope of the line, of the straight line, connecting the 2 coordinates, a comma f of a, that x value and y value, to b comma f of b. Right? That's all this guy actually is, right? So I have a function that's defined on the interval a, b. If I connect the endpoints on that function at a and b, draw a straight line, and find the slope, that gives me the thing that we know as difference quotient. By the way, this line, the line that I'm referring to here, line, still can't write, I haven't fully woken up yet, is called a secant line. Forgot what the etymology is, but that's what it's called. It's called a secant line, okay? So the difference quotient is really the slope of a quote unquote secant line. And this is just a line that connects 2 distant points or 2 distinct points on some function. We call that a secant line. And yeah, that's what this guy is. Now I want you to note that we could change our notation a little bit. Okay, so let's look at the same kind of idea, but now I'm just going to label things slightly differently. I'm not changing the idea behind it, but I'm just going to change the labels that I'm using. Right, so it's my same function f of x. Have my 2 points again, a and b. See how those are perfectly horizontal? It's because I'm making the sound. But I can't do that sound while I'm writing, so my notes look like barely know how to write. Okay, so here's how we are going to label it. Instead, I am going to call the a just x, some x value. And then what I'm going to call the b is I'm not going to call it some other x value, but I'm going to make a distinction. I'm going to want to write b in terms of how far it is from a. So let's say it's a distance h away from a, right? So a and b, these are just 2 points where the distance between them is h, right? So if one is x, the other one is x plus h, right? By that labeling, that would mean that this guy corresponding to b is f of x plus h. And this guy corresponding to A is f of x. And of course, that would correspond to our y2. This would correspond to our y1. This would correspond to our x1. This would correspond to our x2. So now, see, I didn't do the da-da-da, messed up. Okay. So now when I find the slope with this formula, let's say slope of the secant line, let's call it m sub secant now, is going to be y2 minus y1 over x2 minus x1. And in this case, my y2 is f of x plus h, my y1 is f of x. Over my x2 is actually x plus h. My x1 is actually just x. Now, clearly, the x's cancel each other because it's x minus x. And so we get the much beloved f of x plus h minus f of x over h. This is a super important expression. This expression, with a little bit of tweaking, as we will see in a few classes, is responsible for half of calculus. So it's a very, very important expression. And we're like, hey, we should get the algebra kids and pre-calc kids to start working on this because it's going to be super important eventually. And yeah, you're going to see why it's important in this class. But yeah, that's where it came from. This is the difference quotient. Gasp. It's the difference quotient. Yeah, I know you guys are all bursting with excitement, but I'll show that in the notes that this was happening. Okay, that's where the difference quotient came from. It's really just the slope of a straight line, but we have a particular line in mind when we write it this way. That being said, I will also tell you to note in this context, meaning average rate of change, the AB notation is preferred. Because it's much easier to just talk about it in terms of the 2 points A and B, as opposed to talking about it as one point and another point that's h distance away from the first point, right? It's better to just call it, oh, it's point A and point B, right? Is preferred. There are going to be other contexts where the x plus h notation is going to be preferred, but for the topic that we're currently talking about, average rate of change, this is the preferred way to think about it. You can think about the 2 points as their own people. You don't think about one just in terms of the other. So let's actually just do an example, and then I'll talk to you about the interpretation, why we think of this as average rate of change. So let's just do an example. Let f of x equals 4 minus x squared. So that's a polynomial. It's defined everywhere. So it's going to be defined on any closed interval I mentioned. On, let's say for the sake of argument, it's on the interval 1, 3. Find the average rate of change of f on 1, 3. Now, for a problem like this, it's pretty much going to be asked in this way, right? So if I ever test you or quiz you on finding average rate of change, the question itself is not going to be complicated. I'm just going to say point blank, find the average rate of change. Here's a function, here's the interval, find the average rate of change. That being said, chances are on a test, this would not be a whole question by itself because it's not going to be a difficult question. This would like be part A of a question, where in part B, I ask you something else. So it's not very difficult to get through, but it's an important idea and we should know how to do it. So what you'll see here is basically you're just going to note that the AB is the minus 1, 3, that means I'm thinking of my A as minus 1 and my B as 3, right? Now, you don't need to write that, but you should know that, right? So you look at this problem and you say, oh, he's basically telling me A is minus 1 and B is 3. And again, I could have said it in a different way. I could have used inequalities. I could have said for minus 1 less than or equal to x less than or equal to 3, it's the same thing. The leftmost endpoint is your A, the rightmost endpoint is your B, okay? So now you would just go in, average rate of change. That's going to be f of b minus f of a over b minus a. Now, this is a calculus class, which means it's not like statistics or probability class where you would give students a formula sheet. I do kind of expect you guys to remember all the formulas I give you in this class. And so a pro tip for that is to, every time you're using the formula, write it down, right? So eventually you will always remember it. Okay, so there we go. And where are we? Yes, so now we know that our B is 3, our A is minus 1, and this is divided by 3 minus 1. Now, what is f of 3? Remember, f of x was 4 minus x squared, so f of 3 just means I'm going to plug in 3 into the x minus, so that's my first part. Now, I could have put parentheses around this 3. It's not necessary, though, but if you did it, it's totally fine. Usually, there's no danger in overusing parentheses as long as the right things are in the parentheses. Usually, there's a danger in underusing them. For example, in the second part, there is that danger. I should put that -1 in parentheses before squaring it, because you don't want the negative right beside the negative, so you think it turns into a positive, because in this case, it does not. It's a -1 squared, so that becomes a +1, and then you subtract the +1. So leaving off the parentheses here is probably not something you want to do. Putting it around the 3 is optional, though. But if you're someone who you're not sure when you should be using parentheses, then using them all the time is not going to be bad. Okay, so that's actually going to be 4. And right now we're just going to simplify, right? So this is 4 minus 9. This is 4 plus 1 all over 4. Okay, so that's going to be minus 5. See, I fell into my own mistake. This is 4 minus 1. So that's going to be minus 5 minus 3. That's minus 8 over 4, which is minus 2. So that is the average rate of change of f of x on this. And so far, are there any questions on this? Okay, so, all right. So hopefully we're doing okay there. Okay, now what does this mean? Okay, so let's talk about that. Let's talk about the interpretation, why we would even refer to this as an average rate of change. What does it actually mean to say the average rate of change is minus 2? So let's draw the picture so I can visually show you. Here's my function, 4 minus squared. That's a 4. We know that this happens at 2. That happens at 2. And our A and B are minus 1. And that's right here. And 3. Let's put that right there. So, and then that's, okay. So we've calculated that when we are at minus 1, we are actually at 3, right? So that's a 3 here. And when we're at 3, we're actually at minus 5. Okay. Now, let's actually look at the line here. The secant line is that guy. And I can even extend this guy here to be like this right triangle kind of business, because there are some distances that we care about. I want you to notice that if I look at the x distance, how far did we travel? Well, there are 4 units here. X changed by 4 units. Or let me, instead of changed, let's say increased by 4 units. Now, in that same span of time, what happened to the y value? You'll notice that our y decreased 8 units. How do I know it decreased 8 units? Well, it started at 3. Y starts at 3, but y ends at -5, right? So the distance between 3 and -5, there are 8, right? So the point is, as x increased by 4 units, my y decreased by 8. And here's how we can interpret that. X increased by 4, and y decreased by 8, i.e., y decreased twice as much as x increased on average. So, i.e., on average, and I'm going to explain why on average is important to say here. Y decreased 2 units for every 1 unit increase of x. Now that part decreased by 2 units for every 1 increase, that leads to the notion of a -2 average rate of change compared to x. Okay. So every time x moves 1 unit over, on average, the y falls 2 units. And that is therefore represented by a negative. Y loses 2 units, so it's a -2. But this is on average. For every 1 unit increase, y decreases 2 units. Now, why is it on average? You might notice that in the interim, this might not be the case. For example, when moving from -1 to 0, if you look in this interval right here, your y value actually increased. You moved from 3 to 4, right? However, that's just in that little part. If you look on average, most of the time, your y was decreasing. So it might increase and decrease and fluctuate, but then you say on average, if you look at the big picture overall, we fell down 2 units for every 1 unit increase in x, right? So that's why it's on average, because in the interim, in real time, it might be increasing and decreasing, but the average, you look at the entire interval and say, on average, what happened? X increased by this much, or Y decreased by this much. On average, the change in Y over change in X is a -2, right? So that's why the slope can be interpreted as an average rate of change. It doesn't tell you what's going on in the interim, but it tells you overall in this window, here's what's going on. Here's how the change in the Y related to the change in the X. So this is the average rate of change. Rate is talking about how one thing changes in relation to the other. Of course, generally in terms of when people use the word rate, they think of the X value as time, right? So rate means how something changes over time. But that's where the idea comes from, right? It's talking about the rate of change of Y with respect to X on average, right? So that's where the interpretation comes from. And that's why the slope is actually useful here. the calculations you would do for the slope are exactly the same calculations you would do if you wanted to find out how one thing changed on average in relation to the other thing, right? Which is an idea we're going to come back to. It's actually a very important idea, more important than you might realize at this point. But yeah, that's average rate of change, and that's the interpretation. Why is this the formula that we use for average rate of change, right? It's because when we look at the big picture, on average, what's going on, right? Why decrease 2 units for every 1 unit increase in X? So you can say the average rate of change for Y in relation to X is -2. Okay? And the slope formula actually tells us that. So that's pretty cool. Any questions on that interpretation? So we're good, can move on. Okay, and that kind of wraps up this section. So we are now going to move into, I forgot, maybe it's in your book, it's chapter 3. But we're gonna start talking about calculus. So I figured, right, this is why we're all here, right? So let's actually start that discussion by talking about what is calculus? Now, there are those of us who believe that calculus isn't really important, right? There are a lot of people you can talk to where if you ask them, you think calculus is important? Well, calculus is this thing I did in school and I've never used it in my life, so no, it's not important. But that's not how we judge importance, right? Just because you didn't use it in your life, it's not important. That's not how you judge important. Calculus is important. Without a doubt. It's one of the most important endeavors that mankind has ever set out on. And there are a lot of other things that people might think are important that without calculus, we wouldn't have those things. So for scientists especially, they definitely know that probability and statistics are important. Whenever I'm doing experiments and I want to make sure that I'm trying to get rid of bias, and we know that this is the way the universe works, you do tons of experiments, you do statistical analysis, you do a hypothesis testing, you try to test whether your hypothesis was true using statistical analysis, you create confidence intervals, and you say, you know what, I'm 95% sure that this is the correct answer, right? And you set these guys up, and then you might have scatter plots, and then you have to do the best fit line, and then regression lines and all that stuff. And so a lot of scientists would for sure think, oh, statistics is important. But here's the thing. Most of those formulas in statistics you would not have without calculus. How do you know how to find a regression line? Calculus 3 is how you know how to find a regression line. So in statistics, they would tell you, oh, here's a formula for a regression line. And you ever notice that no one ever actually shows you where that formula comes from? It's because usually people who take statistics classes have never done 3 semesters of calculus. And so they can't tell you, right? You need calculus 3 to be able to derive the formula for a regression line, which obviously is very, very important. So there are a lot of things that people think are important. And in the background, calculus is how we know those things. So by extension, calculus is all automatically important. But just to give you a more cutting edge example, so you guys don't think I'm just this old man with boring examples, let's go into something like AI, right? Artificial intelligence. How does that work, right? Oh, it's so mysterious. How does Google know that I wanted these shoes? How does it, what is artificial intelligence? Well, artificial intelligence is basically a computer program that knows how to use probability and statistics to make prediction based on the data that it has. And how does it know how good its predictions are? Calculus. Calculus is how it knows, right? So your AI takes a bunch of statistics to kind of predict, right? It follows your data, which is why data and privacy are such a big deal. It can predict how you would react in certain situations, and a lot of times it's going to think, based on all this data I have on this user, chances are they're going to be interested in this thing, right? And of course, we want to refine it so that it's actually true that you would be interested in that thing most of the time. How would the AI know that that's the case? Well, it uses calculus to minimize the distance between its prediction and the actual reality, right? So then it kind of gauges how useful do users actually find my prediction and my prediction. And the goal is to get this to do that, right? So that my prediction is smack dab on the point. Now, that whole concept of minimizing a distance, calculus, right? And we're going to see that later on. So, yeah, artificial intelligence uses calculus, right? As well as statistics, linear algebra, probability, and of course, computer science, because they have to do the coding. But the way the program works is all about math, right? So that's an example. So calculus is important. Let's hope none of us don't believe that. It's important, without a doubt. It shouldn't even be a debate, really. Okay, so now that we know it's important, what is it, right? So if you tell someone, oh, I'm in college, I'm studying calculus, and they say, oh, I heard about that. What's that about? What is calculus? What are you studying? What would you say? Does anyone know? Did anyone take calculus before and knows what it's about? What is calculus? Is there anyone who took it before? No, we're all new. Okay, all right. So great. We're going to learn what calculus is about. Some of the students in my other class actually took calculus before, and they had some guesses. They weren't totally off the mark, but they weren't as refined as they should be. So let me tell you what calculus is about. So let's start at the kind of mathematical answer, and then we're going to break it down into why would you care about this in the real world. So calculus, like the average high school student who takes calculus would probably say something like this. Calculus is the study of derivatives, integrals, and their applications. Right. So anyone who has taken calculus, they would have spent a lot of time working on these things that they call derivatives and integrals. And they would use those things to do word problems, which is applications. And so they might say, oh, calculus is the study of derivatives, integrals, and applications. But, you know, what is a derivative? What is an integral? Right? Like, so so in a phrase, that's the answer. In a word, right? Someone puts a gun to your head and says, tell me one word what calculus is about. Probably the best answer would be limits, right? Which is a mathematical thing. We're going to talk about what a limit is specifically, but limits would be the one word answer. Why? Because derivatives and integrals are special kinds of limits. So we're going to develop this notion called a limit, and then we're going to develop notions based on that notion that we call the derivative and the integral. Derivatives and integrals are special kinds of limits. Okay. So it's pretty much the study of limits, but eventually, once you use the limit to develop the derivative and the integral, then you spend all your time on derivatives and integrals. Like we use the limits to get to that point, and then we exploit that, right? So limits is where it all began, right? So that being said, how does it? What is the meaning? Okay, so let's actually break it down. So here's calculus. It will branch off into two parts, right? So there's a part of calculus called differential calculus. This is the part that studies the derivative. Okay. Now, what is a derivative? Well, this is sophisticated answer, and we're going to talk about why it's sophisticated soon, math solution to, there's something called the rate problem. Okay. Now, the rate problem is a very vague problem, but it's a very important problem. So here's what the rate problem is. How fast does something change, especially in relation to something else? Now, why is that an important question? And it's a very basic question. Things change all the time in life, right? Law of entropy, right? Things are always changing. And overall, they change for the worse. And human beings and technology are fighting against this entropy of the universe just going into chaos, right? We try to impose our order on it. And in order to be able to do that, we need to know how to measure rates, how fast something changes. So things are changing all the time. The sun rises, the sun sets, plants grow, we harvest them, they grow again, right? The tide comes in, the tide comes out. We look at this world and we're like, things are changing all the time, right? And they are threatening our survival. We need to survive. So what do? We have to start making plans to not only survive these things, but if possible, to take advantage of these things. Now, to be able to do that, we need to know how much time do we have? So the tide is going to come in. How fast does it come in? How much time do we have to make sure that we get out of the way of this body of water? How high do we have to build our ports? So we have all these questions about the tides now, something that we know is happening, but we know that, knowing that within the next 2 hours, the tide is going to be here versus there is a very, very important question, right? How fast is this change happening, right? So that was a very basic, generic, general question. How fast do things happen, right? Which you might say, how can anyone even answer that question? Doesn't it even depend on what you're looking at? And it turns out, not really. We can actually give a general answer to that question. This answer is the derivative. Anything that changes in some continuous fashion that we can plot with a function, we can figure out how fast it's moving with something called the derivative. It does not matter what that thing is. Doesn't matter what context it's in. As long as it has certain properties, we can figure out how fast it's moving. And that's why the derivative is super important. It tells us how to measure how fast change happens. This allows us to make predictions and to prepare for, stuff happening. And it's a very sophisticated answer because the problem itself is so vague. No one would thought there's a single compact, nice, formulaic mathematical answer. Why would there be? There are times when the derivative doesn't help, and we're not going to get into those times in this class. We're going to talk about the cases where the derivative does help, but it helps a lot in many cases, in most cases. And there are times when even if the derivative doesn't help, we can create a model of the situation, a scientific or mathematical model of the situation that pretends the situation work in a universe where the derivative would help, and we can solve the problem with the derivative and then translate the answer back to the real world. So it's very, very super duper important and useful. So that's what differential calculus is about, the study of how fast things change. And the derivative is the answer. When we think about what is the most general, nice, unique answer that we can, different people can ask me the same question about different things and I can give them all one answer. The derivative is that answer, right? A very important thing. Now, there was something else that was important. So there's another branch of calculus. This is called integral calculus. And this had a very different concern. It studies the thing that we call the integral. And this is a sophisticated answer to another problem. Let me write it the same way. Sophisticated math solution to something that's called the area problem. So the area problem is, again, very vague. Basically, it is the general question of how much space something takes up. If that thing is 2D, this is really a question of what's the area. If the thing is 3D or higher, it's what's the volume, right? So takes up space. This means area or volume. So that's the question. And again, it's a broad question. How much space does anything take up? Now, you might think, hey, don't we know that from geometry? Like, I know a rectangle would take up length times width. That's how much space it takes up. A circle, pi r squared. Yeah. So here's the thing. Sometimes they're very odd shapes. We're not talking about nice geometric shapes. We're talking about random blobs, right? How much space does that take up? Where's your formula for that? And if you could figure out a formula for that, I could just draw the blob slightly differently. Do you have a formula for this one? And now you'd have to figure out a formula for that one, right? So now it's like, we want to be able to figure out, kind of like to do geometry with random crazy shapes, right? Is there a way that I can figure out a formula to find the area of something? And that is pretty important. For many reasons, we need to know how much space something will take up. To give a more socioeconomic example, let's say plots of land, right? So way back, maybe I'm a farmer or whatever, I own a plot of land, you know, and to escape the state of nature, we develop a government. Government decides, oh, you know what, I'm going to tax you based on how much land you have. So these are your property taxes, and we tax you 5 pence per acre. So now it would be reasonable, especially if your plot of land is very oddly shaped, for you to ask, how do you know how much acres I have? Like, it's not a rectangle. Like, how did you do that measurement, right? So now it's a matter of, yeah, how do we figure out how much space? Like, if I want to charge someone based on per unit space, how would I go about doing it? And I don't want to have to do that, find a different formula for every person. There are millions of people in our society. We can't go around measuring the plots of lands of millions of, like, we need a better way to do it, right? So that's an example. And it turns out that this had a very crude and but it was a pretty decent solution. Well, the idea is to just break up that blob into shapes that you do know how to find the area of. You find the area of all these smaller shapes and then you add them together, right? So I know how to find the area of a rectangle. Let's just dice it up into a bunch of little rectangles and then do a bunch of length times width and add them up. And of course, if there's a part of this blob, like this corner right here, that's not exactly a rectangle, I just kind of guess, well, that's about a quarter of a rectangle. And you know, and if you want to get more accurate, you just dice it up into smaller rectangles and to get it a little bit more detailed, right? So that was the answer, and that it worked for a long time. And this is actually an idea that we figured out a long time ago. So yeah, so this was the basis for something that we call the integral. Basically, the integral is a way to make this process more streamlined, more where you don't need manpower. Like, every time you want to do this, you don't want to have to like hire someone to dice up the rectangles and count all the stuff, right? And it's just too much manpower, too intensive. Could you streamline this process and make it mathematically sophisticated where it's easier to do this? And the answer was yes. And the answer was the integral. And by the way, you should know that we've been able to answer these two questions for a long time, right? So these two questions were literally important to the survival of the human race. So we've had answers for both of these for a very long time. There is evidence even that Archimedes was doing integration and using integrals back in 400 BC, around there, right? So like literally millennia, we knew about how to solve these guys. However, here is the thing. Why is calculus class a thing? Is because these two guys were thought of as different things forever. Like, you have a bunch of people over here studying how fast things change, and you had a bunch of people over here studying how much space stuff takes up. And no one would ever think that these people are actually working on the same problem from different angles. And it turns out they were. It turns out that the rate problem and the area problem are two different sides of the same coin. And they are intimately connected, right? So the area problem and the rate problem are inextricably linked. And that link was developed around 300 years ago by Newton and Leibniz. So a lot of people think that Newton and Leibniz are the inventors of calculus, and this is why. It's not that they came up with the ideas first. The ideas existed before them for thousands of years, but never before did we realize formally that these guys were actually the same thing, and we could mathematically prove that they are very connected. And studying one problem is the same as studying the other one. I can use what I know about area to figure out stuff about rate. I can use what I know about rates to figure out stuff about area. And it was like, why would those be connected? But they are connected, and it's connected by something called the fundamental theorem of calculus. Now, there's going to come a point in the semester where I'm going to tell you something called the fundamental theorem of calculus. And reasonably, a lot of students see this and they probably wonder, why is that so fundamental? And this is why it's fundamental. It bridged millennia of separate study into one cohesive theory. And that's what Isaac Newton and Gottfried Leibniz are known for. And this is why they're thought of as the fathers of calculus. They are the fathers of calculus as we know it. They're the guys that realize, hey, these two things that we thought were separate are actually connected. And I can actually use my knowledge in one area to affect knowledge in the other. And that was the fundamental theorem of calculus. And Isaac Newton's teacher was also responsible for figuring out like half of the fundamental theorem of calculus. So that's why, so this happened around, around 300 years ago. So a lot of people think calculus was around 300 years ago, started in the 1700s. Not true. We had these pursuits a lot longer, but it took us till the 1700s to realize these two things were connected. And there's a life lesson in here somewhere, of course. A lot of times we study things and we have all this knowledge that we think aren't very useful. And yeah, I took this class and I did that class and I had this experience and I did that experience, but it wasn't useful in my life. And sometimes it turns out things are connected in ways that we don't realize. And it took mankind millennia to realize that these two things were connected. And a lot of people go through their entire lives and not realize connections. There are a lot of people who have this belief, the math I learned in school was useless. And it's like, no, it's connected to your life in more ways than you realize. You just don't have that fundamental theorem yet. And so that's kind of the idea. This is what I think is a very good argument for interdisciplinary learning, right? So if you're an artist, you should know about science. If you're a scientist, you should know about art. Like there's no knowledge that you should write off and say as this is useless to me. Turns out a lot of our breakthroughs happen because of the mixing of ideas. And so there's a very philosophical thing that we can take away from this. Again, to go back to AI, how did the computer scientists figure out that, the math is what they needed? Yeah, it's just like there are things that we didn't think were connected that we were studying in statistics and probability and linear algebra and calculus that we're like, yeah, no one, and especially computer scientists, a lot of computer scientists are actually glad the day they take their last math class. They don't care about math a lot. But then you have some computer scientists who are like, hey, you remember that thing we learned in math class in college? I think we can use that here. Boom, AI happens, right? Markov chains happens, insurance risk happens. All these things happen when we realize these connections. So this is responsible for calculus as we know it. And that's why it's the fundamental theorem of calculus. That's why we're all here. That's why there's such a thing as calculus class, right? Responsible for calculus as we know it. So what is calculus? Calculus is the theory that bridges the solutions to the rate problem and the area problem via two things called the derivative and the integral. These answer some very important questions, and they are highly applicable not only to human beings and society millennia ago, but still even today. And it's very important that we know about this and can take advantage of it. And if we can, it puts us head and shoulders above the competition. Will you use calculus in all its detail in your daily life? Probably not. But if you can find a way to use calculus, you will be better than people who don't. It is something that's worth knowing about. So yeah, that's why calculus is important. That's what it is. This is the studies that it helps us to pursue. And so now that we have the bird's eye view and what we're all doing here and hopefully why it's important, let's actually start to get into it. How do you build such a theory that can answer these questions in such generality? Well, the journey starts with something that we call, as I mentioned earlier, a limit. So let's do that. Now we're going to spend a couple classes on limits. Okay. So at first, you're probably not going to see how does this connect to any of that other stuff I was talking about, but there's going to come a point where I'm going to show you how it connects. So in Calculus 1, we spend most of our time on differential calculus. So 2/3 of the class is going to be spent there. So we're going to develop things that we call the limits. I'm going to show you how to use limits to derive the thing called the derivative. Then we're going to spend a lot of time learning about how the derivative works and applying it to different situations to solve problems. Then I'm going to talk about the area problem, and then I'm going to use limits to develop something that's called the integral. And then I'm going to show you the fundamental theorem of calculus that tells us that there's a connection between the two. And then we'll spend the rest of the time on integrals, right? But that's the very small amount of time towards the end of the class. Usually we study integral calculus in great detail in Calculus 2, which a lot of you don't have to take, so you'll probably never get to experience that. But that's where integral calculus gets taught, at least in 2 dimensions and less. Calculus 3 does both of these guys, but it puts you in 3 dimensions, and Calculus 4 goes higher dimensions, right? So once you get to Calculus 3, that's where you can start applying calculus to statistics and these other things. But for now, we're just learning the basics, how we can answer very specific problems. The journey starts with limits, and there is a very mathematically rigorous definition of limits called the epsilon delta definition. But really, you only need to know that if you're like a math major or maybe a physicist or a special kind of engineer. Most people don't need to know that definition, so I'm not going to tell you that definition. I'm going to tell you a more intuitive layman's definition. We give an intuitive definition of what a limit is. Okay, so it's a fuzzy definition, not really a mathematical definition by any stretch of the imagination. Okay, so here's what a limit is, and it's a very nuanced idea. It's going to sound simple when I say it, but it's actually quite nuanced, and you're going to have to do a bunch of examples to really get it. Let's actually say what that is. Let f of x be a function. We say the limit as x approaches a of f of x is L and write this expression, right? So this is the sentence I would use to describe the notation I'm about to write. The limit as x approaches a of f of x is L, right? So we'd say the limit, Lim, as, that M is so bad. The limit as x approaches a of f of x, so the f of x is right beside that, is equal to L, right? So this says the limit as x approaches a of f of x. So that's what we write, and that's how we say it in English, right? The limit as x approaches a of f of x. Of course, equal means is, and then L is L. Sure. It's just L, right? Okay, so we say this phrase and we write this notation. And what does someone mean when they say that? To mean, as x gets close to a, the y value, f of x, gets close to a unique, unambiguous value L. Okay, so that's what it means. So we write this notation, and what it means is, as my x value gets close to some number, my y value will get close to this number, right? So as my inputs get close to something, my outputs will get close to something, and I can tell you what that thing is without any ambiguity. And that's basically what a limit is. So, i.e., the limit is the y value. The limit is what the y value gets close to. As the x value gets close to something. Right? Now, why is this not a mathematical definition? Because it's too vague is the basic answer. A mathematical definition should not be up to the interpretation of the reader. So it's not like a law where we need like a Supreme Court judge. Every mathematician should be able to read any math definition and we all come away with the same interpretation unambiguously, right? It's, for math, that is very important. We cannot have anyone not agreeing. That's very important. So why is this? Because get close is very ambiguous, right? Different people will have different ideas of what close means, right? So this is why some people, not meaning offense, will kind of invade your personal space and really get close, because what is too close to them is not what's too close to you, and you have to tell them, hey, you're too close, right? So it's like, what some people think is close is not what other people think is close. So when I say get close, what does that really mean, right? When you say unambiguous, what does that really mean, right? These are words where it's like, in English, different people think of it, is 1 unit close? Is a half a unit close? Is 0.00001 of a unit close? What does close mean, right? So that's what, and the mathematical definition is arbitrarily close, which basically means as close as anyone wants. So it kind of takes anyone's expectations and it basically wants to define it in such a way that it will satisfy anyone's definition of what close really means. And there are a lot of math symbols that go into defining that unambiguously. So you can define what close means without ambiguity, but we won't need to know how to do that. So that's what I really want you to get from it here. So I want you to know the notation. I also want you to have this idea in your head. When you're looking for a limit, you're looking for a y value. You're looking for the y value your function is getting close to when your x value is getting close to something. And that is what I really want you to get. That's the concept that's going to make you really understand what a limit is about. So let's actually do some examples. And we can start to talk about, start to really get what this definition is trying to say. So let's do some examples. And again, we're going to expand on this. We're going to do more complicated examples. I'm going to give you properties of limits, and that's all going to be good. But for the next 15 minutes or so, yeah, I have about 15 minutes left, I think. For the next, I have about 15 minutes, right? We end at 9:45. I'm pretty sure. Okay, so for the next 15 minutes, I'm just going to give you a few examples to slowly kind of get you into the idea of what a limit is about. So let's say I ask you, A, what is the limit as x gets close to 2 of the function 3x minus 1, right? What's that? So I write down this expression, lim x arrow 2, 3x minus 1. What is that? What does that mean? What is the answer? How would I know that that's the answer? Well, let's actually see. Now, on a picture, what would be happening? So 3x minus 1, this is a straight line, y-intercept minus 1, slope positive 3, so it's going to look like that. Right? So this is the line y equals 3x minus 1, right? Which we can call f of x if we wanted to. Okay, now what is the intercept here? So the x-intercept is when y equals 0, so that's going to be like a third, right? But I actually care about the value 2, right? So here we are at 2. So now the question is, as my x value gets close to 2, what happens to the y value, right? That's the question. So I can say, okay, what if I get close to 2? Okay, so let's say we're walking on the x-axis and we're walking and we're getting super close to 2. How close? Close as you want. Get closer, get closer, get even closer. So we're getting very close to 2. And so now we kind of track this up to the function and we say, okay, so as I get close to 2, it means I'm on the function and I'm moving in this direction. And so now I'm like, okay, the focus should be, what is my y value getting close to? Right? So at the same time, my function, the output is behaving like this. The output is getting close to some value, right? That value is the limit, right? So the limit is the y value we're getting close to when our x value is getting close to something, right? So as I get close to 2, it's getting close to that. And then someone can say, okay, well, what about over here? Because I could get close to over here. And again, okay, if I'm getting close to 2 from that side, it means I'm on this part of the function, mapping up, and I'm getting close to that, right? And then I can translate this over to the y-axis, and I realize that, okay, this means I'm heading down here. So you'll see that as I close in on 2 on the x-axis, I'm closing in on some value on the y-axis. That value is what I'm interested in. I'm interested in the y value. So that's why this concept is important, right? What is the y value getting close to when my x value gets close to something, right? So I'm interested in what is the value in that blue box, right? As my x values get close to 2, what are my y values getting close to? I need to know that answer, right? And it needs to be unambiguous, right? Can anyone guess what that answer would be?
5.
5. Yeah, pretty good guess. Let me write it in blue. 5. So we can say limit as x approaches 2 of 3x minus 1 is 5. Yeah, that's the answer, right? Now, you might say, well, we could just plug into, right? Why the need for limit? Right? So you might be saying, okay, so if my x value gets close to 2, I could just plug in 2 for x, and then I would get 5 as the answer. So everyone knows the answer is 5, right? Am I missing something here? Why is this important? And the answer is, we won't always be able to plug in 2. Here's an example. So, and I'm not talking about 2 specifically, just in this example, but just to kind of keep things together, I want to give you another example with 2, I guess. What is the limit as x approaches 2 of this function? So now you might have said, dude, why develop a whole new concept? We could just plug in 2 and get the answer. Okay, my guy, deal with this one. You're going to plug in 2? Well, that would cause a division by 0, right? Yeah, so now what, right? And you might say, well, doesn't that mean the answer is impossible? Well, no, it does not, because again, of how the limit was defined. Get close, which means I don't actually care about being at 2. For this function, I cannot be at 2 because I would cause a division by 0. I just want to get close to 2. Now, I can't figure out what the answer is by actually plugging in 2 because I can't, right? So let's actually examine this guy. What would the graph look like for this one? Any guesses as to what the graph would look like? Anyone? Bueller?
It would be some kind of like curved graph.
No, it's not curved actually.
It's linear?
It's actually a linear graph. Like, how would I know that? Okay, so let's figure that out. So here I have my f of x is x squared minus 4 over x minus 2. And obviously my x cannot be 2, right? Could you express that in a more convenient way, maybe? Something that you think would have the same answer?
You would factor it, and then you could cancel out the x minus 2.
Right. We have a difference of squares in the top. And technically I can cancel out that x minus 2, but still, x minus 2 did not work in the beginning, so it still can't work, right? I'm just rewriting the function, but I'm not changing the function, right? So it turns out that this just looks like the graph x plus 2, except I cannot be 2 itself. Now y equals x plus 2 is actually a straight line, right? Passing through 2 with slope 1. But here's the thing. Smaller eraser. I cannot actually be at 2. So at 2, you'll realize that there's a gap here at 2, right? So the graph looks like a straight line, but I can't actually plug in 2. However, the line x plus 2 gives me all the same values as the original function, except at this one point. So there's a gap at that point. It's called a hole, actually. That's the technical phrase that math people use. It's a hole, right? This is called a hole, right? And now we can play the same game. So this here is my actual graph, f of x. It's like a straight line, but it has a hole when my x is 2. But let's play the same game. As I get close to 2 here, that means I'm on the graph climbing up to this hole, which means the y value is climbing up to there. So we're getting close to what that hole would have been had it been there, right? So it's not actually there. So I can't actually get there, but I don't care about getting there. I only care about getting close. Similarly, someone can come over here. All right, I'm getting close to 2 from over here. I'm coming down here. And so that translates to me moving here. And so now, again, just like the last time, as we get close to 2, we can never actually get at 2. I can never actually plug in 2. But as I get close to 2, clearly my y value is getting close to something as well. What is that thing? What would you guess that number is?
We're be getting close to 4, but not equal 4.
It would get close to 4. Yeah, it will never get to 4, but the closer you get to 2 would be the closer you get to 4, right? So it's important that we never actually get there. That's what confuses students sometimes. They think that it just means, oh, we can get here and go here. But no, it's all about getting close. We never can actually be at 2, and so we can never actually get to 4. But 4 is what we would get closer and closer to if the x values got closer and closer to the number 2. Okay, so here I can say the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to 4. Now, I'm going to tell you a shorter way to figure out that answer. Don't worry, but I do want you to get the concept. And for that, I need to explain this at length, right? We're going to basically figure out how to get to 4 very quickly. And essentially, these are the calculations we're going to use to figure it out, right? So we're going to basically simplify it to get x plus 2 and then realize, hey, I can plug in 2 into that guy. And then we're going to plug it in and get 4. But for now, it's very important that you understand, back to stroke eraser, very important that you understand the idea that it's not important to actually be able to plug in 2 to be able to have an answer. I really want you to get that. So the idea is very nuanced. Let me leave you with one other thing, and you guys can tell me what you think the answer is here. So let f of x be this guy. A piecewise function. Ooh, okay. What is the limit as x approaches 2 of this function, f of x? Now, since we're almost out of time, I'm just going to sketch it for you guys. Hopefully you remember how to sketch piecewise functions. And the idea basically is you sketch it in pieces, right? So here's the 2, and you know that something it's one way for one side of 2. So if we're less than or equal to 2, we behave like the function y equals x minus 2 squared, which is like y equals x squared, but it's shifted over by 2 units. And so when my x is 2, that guy is going to be 0 pretty much. And then it's going to be a quadratic kind of going off like that, right? So that's the left side, right? So when we're less than or equal to 2, that's it. Now for the right side, we want to get 3x plus 1, which we know is a straight line with y-intercept 1 positive slope. Now, if I plug in x equals 2 there, I would get 7. So this here, this would be where if my x equals 0, my y would be 4. So this would be at 4, which means at 7 is where the other graph would start. And that's just a straight line moving up. So this is the picture, right? So now I want you to notice that when we're at 2, we're filled in here. So the answer is 0 when we're at 2, okay? So now, if I were to ask you, what is the limit as x approaches 2 of f of x? Okay, So that's the picture. What would you say? Ideas? So this is really testing if you know that definition, which hopefully you guys all wrote down. It's right here. Hope you guys wrote that down, right? So now really think about the definition and give me your guess. What do you think? Just go, tell me, because we're pretty much out of time now. So just tell me so we can all go home. Well, we are home, but you know what I mean.
Would it be like two answers where like you do like 4 and 7 or?
Ah, could it be? Let's look at our definition. See this part of the definition? Unique. So no, there cannot be two answers. Okay, so now what? So knowing that there cannot be two answers, what do you think?
Is it undefined?
Undefined, yes. There is no answer to this question. Now, when it comes to limits, we don't say the word undefined. The phrase we use is does not exist. The limit does not exist, and we write DNE, right? And that stands for does not exist. Right? There is no unique, unambiguous answer. One person can say, hey, look, if I get close to 2, my Y value gets close to 7. But then another person could come and say, no, look, if I get close to 2, my Y value, and I'm on the function right here, my Y value is getting close to 0. So someone can say the answer is 0 and the answer is 7, and we can have two sides split up, you know, like we have pitchforks and like the answer is 0, the answer is 7. We have two groups. The fact that there's a disagreement is in and of itself a problem. It needs to be unambiguous. It needs to be unique, which means if there are two possible answers where you can give a good argument for both, then there is no answer. Now, there is a thing that we can use to describe a situation like this happening, which we'll talk about next time. But overall, for the concept of a limit that we've developed, this does not work. So I will leave you there to chew on it. To deal with this, we develop a concept called one-sided limits, and we'll talk about that next time. We'll also talk about infinite limits and how we throw infinity into this concept. But for now, that's the concept of a limit. And it's very important that you just know the concept in these terms. It's all about getting close. You don't have to get there, and you might not be able to get there. And you have to get there in a way that is unique, unambiguous. Everyone would have to agree on the same answer. If the mere fact that there are several possible answers means there is no answer for the concept that we're developing. And that's very important. A lot of people, which I'm glad you guys didn't fall into that trap, would have said 0 is the answer because they see that it's filled in at 0. But again, you have to remember for limits, we don't care about being at the point. We don't care who's filled in or not. We care about getting close and being able to tell you what the Y value is in an unambiguous, unique way as we get close. And if we can't do that, the limit isn't a thing. And we say the limit does not exist. We will end there and pick up with more examples and more about limits and how to calculate them easier next time. But for now, we'll end there. Unless there are any quick questions before we go. Okay, so that's it. Thank you for your attention. Have a good rest of your day. And I will, I guess I will see you guys in the next one. Ciao.